the general idea of what I'm going to present is to show some control designs and some applications that have a micro-macro aspect. And we, in fact, are going to consider what we call transport systems in general. So all systems we are going to consider will have some transport phenomenon that will be the main dynamic phenomenon. And we are going to also consider implementation limitations, like, for example, quantization effects. Okay, so I want to say first that these are results that developed within the ERC grant Sinora. So I'm grateful to this as well. And I will, of course, the credit for what I'm going to present goes to the research team. And here we are 3 postdocs, 4 PhDs, and 1 senior staff. There are mathematicians and electrical engineers mainly, and there is also a student from physics. So this is a so people are coming from different backgrounds, and they also originate in different countries, something which is I'm pretty proud of. So we have 5. So Greece is actually the minority here. Okay, so there are 4 topics I'm going to present. So I will talk about control of systems with delays and quantization, and control of systems with delays and switchings. So these are results developed by Florian Kudohor, he's a postdoc here, and Andreas Katsanikakis, he's a PhD. And then I will also talk about control of large-scale hyperbolic PDEs. These are results developed by Yuka-Pika Homaloya, who is a postdoc here, and Lefteris, Dimitri Lefteris is a PhD that started recently. If there is time, I may talk also about how to apply delay compensating control strategies to connecting automated vehicles. These are results developed by Hossein Sami, he's a PhD here. And I will talk about 2 particular applications. One is macro control of epidemics transport. And these are results developed by Bekiaris-Liberis, who is a professor in numerical mathematics here, and Nicoleta Hadzihabi, who is a PhD student. And I will also talk about blood flow stability in the presence of stenosis. These are results developed by Santanu Singh, who was a postdoc here. Now he's in France, a postdoc in Nantes. Okay, this slide is just to provide some very high-level motivation of all these results. So we would like to consider to develop controllers and observers for systems that can be recast as transport systems. So the main dynamic phenomenon that describes these systems is some transport phenomenon. In general, not necessarily transportation systems. So the features that we will address is systems that are large scale. Control is applied with limited information and the control authority. They are complex dynamically, and control actions are heterogeneous, so they may be applied at different system levels. And the challenges for developing controllers for systems with these features is computational complexity that we would like to address, the interaction of the digital effects and the continuum nature of these systems, and the fact that control may be applied at different implementation levels, I mean micro and macro levels. Okay, so the topics I'm gonna talk about, I already explained. So let me start with the topic of blood flow stability in the presence of stenosis. So, okay, some extra motivation, particularly to this problem. Arterial stenosis is, of course, is very important and is the primary cause of human losses. So it will be great if one could have some algorithms to accurately and timely detect such potential threats. So current technological advances, at least according to literature, um, um, support feasibility of advanced estimation algorithms. So for instance, there are smart implantable and not invasive and non-invasive devices transmitting information of blood flow and blood pressure, for example. And we would like to consider one-dimensional models. So one-dimensional models on blood flow, again, according to literature, are accurate enough, at least for the purposes of capturing the main transport and wave propagation phenomena. Of course, blood flow evolves on complex 3D domains and so on, but there are one-dimensional models that have been validated with real clinical data. And we would like now to address blood flow stability in the natural domain of blood flow, which is continuous in time and space. So here I'm going to present some modeling aspects and a stability analysis of a one-dimensional blood flow model in the presence of stenosis. But this is a first step for developing observers and identifiers for these systems. So of course, okay, we need to continue models for this application because, for instance, if there is a stenosis at the point where you spatially discretize how, which you don't know where is a priori, then this may be lost. So we really need to address this as a PDE system. So okay, so here, as I said, we are going to, I'm going to present some elements on the modeling and the numerical solution of this model, and we will study Lyapunov stability. So the framework we consider is blood flow in 1D, and we will describe the dynamics of the cross-sectional area of an artery averaged over the other two dimensions. And V will be the speed, the blood flow, blood propagation speed. So this is a simplified one-dimensional diagram. So in general, as I said, because this would like eventually to use this model for observer design, the measurement that one can have in such an application is pressure and flow. Let's say at some inlet point of a considered artery. So this is technologically feasible with implantable and non-invasive devices. And the ultimate goal is here to estimate three unknown parameters. The location, which is the location, the length d of the domain in which we consider this PDE, the section area of the stenosis, and the length of the stenosis. That will be the unknown parameters for one to identify. Now, we don't solve this problem. We start with the modeling and the stability analysis first. So the model equations look like this. So these are standard mass momentum conservation equations for cross-sectional area and speed of blood. On the left boundary, there is an inflow coming from some upstream arterial network, and P is pressure. So to complete this modeling, we need to also describe pressure, and here we do it with a static relation with respect to the cross-sectional area. So this is a model that exists in literature, and there are some parameters that are related to the material properties of the artery. So this can be considered as known. Okay, so in this model, now I would like to describe how stenosis, to describe the effect of the stenosis. So we will actually, the main idea is to consider the stenosis as a boundary static bottleneck motivated by what one may use in traffic flow. So the assumption is that the stenosis section is constant and small enough. Flow is conserved through the stenosis, and we consider the case where the length is very small, so essentially 0. So with these assumptions, then we need to describe the boundary conditions on the right, which capture the effect of the stenosis. And the effect of this flow bottleneck of the stenosis, we capture it with a pressure drop at the right boundary. So this is the pressure drop. This is analogous to V squared, to the kinetic energy. And we need one more equation to make this a proper boundary condition for the hyperbolic system with states A and V. And this is a relation that describes the difference in pressure before and immediately after the stenosis, where after the stenosis, we describe pressure as being analogous to the flow. And this parameter RT describes some terminal resistance, which actually depends on what we consider that happens downstream of the arterial segment we consider. So this can be, again, considered as given because it depends on the scenario we consider. Okay, now with this, we can actually write down properly boundary condition for the right boundary of the hyperbolic system. Okay, one can rewrite this in the Riemann coordinates. So in this application, there are the system is heterodirectional. The transport speeds have different signs. So this is for physiological conditions. Okay, and then one gets at the end a system that looks like that. So there is the UV states in the Riemann coordinates. There is a boundary condition on the left that depends on some inflow coming upstream. And then one can formulate a right boundary condition like this. Now, what we did with this model is some numerical simulation to see how this system evolves. So we applied an accurate finite volume scheme. So on the left, you see the flow at the stenosis for different percentages of the stenosis. So as the stenosis increases, the peak of the flow decreases, and the response, the dynamics become slower. And you observe also this in the pressure drop. So the pressure drop increases as the stenosis degree increases, and again the dynamics become slower. So from these simulations, we observed some stability or better contracting property of the solutions, which we would like to now analyze. So in fact, from a medical viewpoint, there are some diagnostic indices that one can obtain from the time constant of the dynamics of the pressure drop in the diastole phase. This is the diastole phase, and measuring the maximum and minimum value of the flow. So for us, now for studying stability, we actually obtain this result. I'm sorry. So what we did is we assume we have a trajectory, a reference trajectory. This reference trajectory is time varying because the inflow may be time varying. For example, it may have a typical shape corresponding to heartbeats. And we have given some trajectory U star V star. So we prove that it is exponentially stable in L2, provided that these conditions are satisfied. So for this, it is better to show you a plot and explain. I mean, okay, the stability proof relies on linearization of the original system and using this Lyapunov function. So what is interesting and is related to the diagnostic index of the time constant of the pressure drop is this plot. So this plot shows the estimate of the decay rate of the solutions with respect to the stenosis. So when the stenosis increases, everything happens slower. And this is due to the capacity decrease at the boundary bottleneck, basically. Okay, so here now, as next step, we would like to actually prove the contracting property we observe. So we proved here only stability of a given reference trajectory, and we would like to also perform the analysis in a nonlinear setup. And the ultimate goal of this is to actually design an adaptive observer. So basically to design an adaptive observer for estimating the unknown parameters, the stenosis degree and the location of the stenosis. Okay, now I will discuss some other application. So now I'm going to talk about macro modeling and control for epidemics transport. So here, what we do? So we will consider epidemic spreading by describing people transport, and we will use a crowd flow model. So the motivation for this is because the main macroscopic phenomenon in epidemic spreading is people transport. And then we would like to use such a macro computationally tractable model to do some tests that are representative of applying macro control measures. So what are these macro control measures? So one could develop such macro control measures for mitigating epidemic spreading through controlling people transport. For example, through manipulating people average distance and speed. Another macro control measure may be by manipulating ventilation rate. And of course, okay, if there are vaccinated or masked people in the crowd, this also is beneficial for epidemics spreading. And we would like to also do some data-based validation of the considered model. Okay, this is to intrigue with you a bit. This is a map, maybe the first map that describes epidemics transport in different regions. This is in a book in the 1650s by a cartographer, and this describes the spreading in different regions during the plague of Athens. And as another example on how old is the problem of describing epidemic transport in different regions, this is a map in Paris from a cholera outbreak that shows the different color bars shows the different number of deaths per 1,000 inhabitants. And this goes back to 1832. Okay, so what we do here is we will consider a macroscopic model that has three components. The first component is a component that describes crowd flow. So we have the density rho of a crowd in a closed space, for instance, a walking facility with one exit. And V is the average speed of pedestrians. And we consider this crowd flow model. This is a 2D version, for example, of what is called Payne-Whitnam traffic flow model. So it describes conservation, has two equations for mass and momentum conservation briefly. So Here, P is a pressure. So for us, this can be viewed as dictating average distances of pedestrians. And capital V is what is called a fundamental diagram relation. This indicates some desired equilibrium speed of pedestrians. Now, these equations also need a direction of the desired movement of pedestrians. This is the vector mu, and this satisfies Hamilton-Jacobi equation. And this equation simply describes the fact that pedestrians tend to move where this term is minimized, so where the travel time is actually minimized. The second component of the model is a component that describes transport of people per category, susceptible, exposed, infected, and vaccinated. So how each people in each category moves. So these are transport equations with the same speed of the crowd. And there are these interconnection terms. This can be viewed as a PDE macroscopic version of a CISV compartmental epidemics model. Now, here, for our purposes, because we consider small time scales, we consider that the only interaction can be between susceptible and exposed. So a susceptible individual can become exposed and nothing else, no other interaction can take place. And the third component is a component to describe the ventilation airflow field in a room. And this is a diffusion equation which has different components. So this is the airflow field imposed by a ventilation. Sigma is a diffusion coefficient. Nu models how fast particles settle on the ground, and this is the effect of the infected individuals. So this is like the beta, an analog to beta coefficient in typical compartmental epidemics models. So, okay, now these three components, what we did is to solve them numerically. So we applied a finite volume scheme. So there are many details here that actually I'm going to skip. For the equal equation, we use some method called fast sweeping method. So there are many details I'm going to skip. So, and then, okay, we consider some parameters that are realistic also according to literature. And I would like to show you now some simulations of the scenarios we consider for running this model. So here we see the ventilation airflow field. So we consider two cases where pedestrians move along and against the airflow field. So this is the room, and there is an exit here on the right. So these are the simulations results. So you see on the top is total density at different time instances. In the middle is the infection coefficient that is responsible for people becoming exposed from being susceptible. And on the bottom is the density of exposed individuals. So what happens here is pedestrians start moving towards the exit. And at the same time, some susceptible become exposed. And this is the scenario where people move against the ventilation airflow field. So I will explain what we observed. Let me show you also a video. Okay, this is the video that shows how pedestrians move towards the exit and how this infection coefficient varies and how pedestrians become exposed. All right, so you see there is this clogging congestion effect at the exit. Okay, now what we concluded, so this is a plot shows the percentage of exposed pedestrians when we varied the following things: the maximum walking speed of pedestrians, the C0 coefficient of the pressure, which actually regulates average distances between pedestrians, the flow rate and the flow rate of the ventilation. Now, this is a pretty busy plot, so let me just summarize what we observed. So, what we observed is that by increasing C0 is beneficial for epidemic spreading because in general it leads to higher average distances. But this also depends on the capacity of the exit. So if the exit is very long, this may not have a significant effect. Increasing the maximum walking speed of pedestrians is also beneficial for epidemic spreading because in general it leads to smaller evacuation times. But again, this is not always true because this depends again on the capacity of the exit. And if the exit doesn't have enough capacity, severe congestion or clogging effects may appear, which are not beneficial for spreading. When we incorporated one extra component in the different densities, namely of masked or vaccinated individuals, this decreases the total number of exposed individuals. And we observe that airflow, ventilation airflow against the direction of movement of the pedestrians is in general better. But this again depends on the size of the crowd and the size of the domain we consider. And increased ventilation rate in general decreases the number of exposed individuals. So now what else we did is to use and utilize some microscopic data to extract macroscopic quantities with the ultimate goal to calibrate the model I presented. So what we did is we took people trajectories from a football match. This is 2019, before COVID, and we consider these trajectories as microscopic data, and we did some computations to obtain macroscopic quantities. And with this, we would like to calibrate with this real data the model presented. So this is what we obtain, an example of what we obtain as total density and exposed density based on the macroscopic data. The macroscopic data is people trajectories. Okay, so what we are currently doing is we are trying to calibrate the model with the data we extracted, the macroscopic model. And we would like to actually choose the potential manipulated variables such that C0 and Umax in a systematic feedback manner. Okay, so the next thing I would like to talk is now a bit more abstract, so a bit without focusing on a particular application. And this is to develop computationally tractable controllers for large-scale hyperbolic PDE systems. So, okay, some specific motivation for this problem is why we would like to consider large-scale hyperbolic PDEs, because these may describe blood flow in arterial networks. So there are hundreds of arteries, each one described by a 2x2, for example, hyperbolic PDE system, or in epidemics transport in different regions, or there may be large traffic flow networks, large water networks, and so on. Now, the main idea we use here is to start with an interacting large-scale PDE system, obtain a continuum, design a controller on a continuum, and then prove that the controller developed based on the continuum works on the large-scale PDE system. So this is an idea that has appeared in ODs, but it hasn't appeared before in PDEs, for PDE control. So the class of large-scale systems we consider is the following. So these are n+1 systems where n PDEs transport, n PDE states transport on the left and one on the right. And these terms may create, these feedback couplings may create instabilities. So we consider this large-scale transport. So we assume, we consider the case where n this is the number of used states, is potentially large. So the solution to this, the stabilization problem of this system is given, for example, by backstepping, and this is the control one obtains. Now, for implementing this control, one needs to solve n+1 equations for the kernels, and these are the equations shown here. But if n is very large, so computational complexity of computing, of solving these in general large-scale kernel equations grows with n. So instead of doing that, we would like to replace the 1 plus n equations with a 1 plus a continuum of equations. And this continuum equation can be derived by considering a proper continuum system, which we prove that really approximates the solutions of the n+1 system when n is large. And this is the equation for the one continuum kernel, which is now evolves on a 3D domain instead of a 2D domain, but is a single kernel, plus the kernel we actually had before. And now, if one uses this kernel for stabilization of the original n+m system, one has a controller with a kernel that can be computed with a complexity that doesn't grow with n, is O of 1. Essentially. Okay, so the idea is to get this, construct this continuum kernel, then sample this continuum kernel and design a controller based on the sampled version of the continuum kernel. Now, if these sample kernels are close to the original kernels, then we can show that this system remains stabilizing. And actually, we show this by letting n to be large. Okay, so this is the theorem. So under some typical assumptions on the parameters for typical on backstepping assumptions on the parameters, if we can connect the parameters of the continuum version of the system, the continuum counterpart, which we can always do. We connect the parameters of the continuum system with the parameters of the large-scale n plus n system in this way, then we can actually show that for sufficiently large n, the controller design based on the continuum kernel is stabilizing. Okay, the proof goes as follows. So, okay, I will just very briefly describe the main lemmas. So, we start by defining in a piecewise constant manner a sequence of parameters. And for this sequence of parameters, we show that we can actually obtain a sequence of kernels that match the original kernels in a piecewise constant manner with respect to an ensemble variable y. So that is the first step. So I'm skipping these details. And then what we show next is that this sequence of kernels converts to the continuum kernel I presented, provided that the sequence of the respective parameters converts to the continuum parameters of the continuum system, or of the continuum kernel equation, if you wish. And this actually happens when n is sufficiently large. So here I'm just showing you a plot which illustrates how the parameters of the large-scale n+1 system converge to a continuum when n is sufficiently large. And in the third step, what we do is we rewrite the original controller as the controller that we constructed based on the n+1, kernel equations, plus some error terms that we can prove that they are arbitrarily small when n is sufficiently large.
Nico, in the previous, when you showed the plots, the previous ones, yeah. Are these obtained by a software package like Mathematica or MATLAB, or by its analytical, like numerical result?
This one?
Yeah, all of these plots that you...
Yes,
because
yes, these are with MATLAB.
MATLAB, okay, thank you. That's what I want.
Okay, so all right, here now I'm just illustrating some convergence video showing how the sequence of kernels converge to the continuum control kernel. So you start here, and as n increases, you actually converge to this continuum kernel. Okay, so all right, I'm against keeping the proof. So at the end, one can express the control like this, where delta k can be shown that is sufficiently small when n is sufficiently large. Okay, so here is a numerical example. So this is an extreme numerical example in which the n+1 kernel equations don't have a closed form solution. So computational complexity may grow with n, but a continuum approximation actually has a closed form solution. So the continuum-based kernel can be computed instantaneously. So this is a continuum kernel, given in closed form. So when n is sufficiently large, one can use this kernel whose commutation is instantaneous to stabilize the system. So here I show, for instance, this is the control input for various values of n. So for small n, stabilization may not be possible to achieve with a continuum based kernel, but as n increases, the system is stabilized and the performance converges to the nominal performance employing the nominal n+1 kernels. And here we show how the controls converge to the exact control based on the n+1 kernels. Now, exact is not really an exact wording, but because the exact kernels are computed with finite difference. And this just shows how computational complexity may grow with n if one goes to solve the n+1 kernel equations. Okay, now another thing we did is to use power series to compute the continuum kernels. And we also tried, I'm skipping all this, and we also tried to identify some class of systems for which closed form solutions are possible for the continuum kernel equations. So, with this may be useful to have closed form solutions for stabilizing continuum-based kernel. Okay, and what we actually did is we extend this to n+n systems. We also extend this to observer-based, continuum observer-based design. And we are now working on the case where one may have m control inputs and this m may go to infinity. So there are some technical challenges there because we change the input space may change. Okay, and this is the last thing I'm going to talk. Here I'm going to present delay compensated controllers for linear systems with input delay, which are subject to quantization and for switched systems. So I will start with the problem of input delay compensation under quantization effects. So, okay, quantization is a digital effect in feedback systems that we would like to address. And switching may also appear simultaneously with input delay. So, for example, consider vehicle dynamics where input delay may come due to engine response, and there is a switching between deceleration and acceleration dynamics. Okay, so we will consider this class of systems first. So here we will consider linear systems where the measurements or the control input may be subject to quantization. And we will consider dynamic quantizers. So we consider quantizers that can adjust their range or error dynamically in real time. And this can represent, for example, a camera where there is a zooming variable that one can zoom in and zoom out. The quantizer satisfies these typical properties of a quantizer. So it may saturate for large states or it has an error delta. Now, in the infinite dimensional setting, we are going to consider these properties with respect to this norm, which is the Euclidean norm of the state x and the subnorm of the actuator state u. For example, this Q with a pointwise definition with respect to u of x is such a quantizer. And here, for technical purposes, for establishing well-posedness, we have to assume that the quantizer is a local ellipsis function, Now, this may appear as restrictive. Actually, it is not as restrictive as it appears because one, for instance, can consider such an approximation of a quantizer with an epsilon layer and can arbitrarily approximate a quantizer that is piecewise constant. And actually, the stability analysis or the design does not depend on this assumption. So this is a technical assumption for guaranteeing well-posedness. Now, why we need to why we consider dynamic quantizer? Because without a dynamic quantizer, we cannot achieve a global or asymptotic stability. So if we fix a quantizer with small range, then the state, if the initial condition is large, may just grow unbounded. And so the quantizer saturates. That's why U remains bounded. And if we have a fixed large range of the quantizer, which may imply a large error, then asymptotic stabilization is not possible. So the system doesn't grow, the state doesn't grow unbounded, but it enters in some kind of limit cycle. So to achieve global asymptotic stabilization, we will consider a dynamic quantizer. So the main tool for delay compensation will be predictor feedback. So in a system without quantization, this amounts in constructing a predictor feedback controller, namely starting with a nominal linear state feedback controller that stabilizes this system when D is 0. Then one modifies the nominal controller to use the future values of the state. So these future values can be given through the variation of constants formula with the formula in the brackets. Now we get this idea and we modify it to account for quantized measurements. So we are going to consider a PDE representation for the system because it turns out to be more convenient for the analysis. And the design is shown here. So we get the nominal predictor feedback controller and we design this zooming variable mu. So essentially this is a quantized version of the predictor state where its measurement is substituted by the quantized measurements, and we choose mu in a piecewise constant manner. So actually what this does is that initially you increase mu so that the state gets within the range of the quantizer, and then you decrease it so that the error of the quantizer goes to 0. Now, to prove, the main challenge is to actually prove closed loop stability. And the theorem we obtain is when the error over the range of the quantizer is sufficiently small, then we get global asymptotic stability and we can derive such an estimate. So this is not exponential stability because actually we have the initial condition depending on this estimate through a nonlinear function, still class K infinity function, but a nonlinear function due to the quantizer's nonlinearity. Okay, the proof strategy goes as follows. Again, I'm skipping these details, just I will give the main idea. So we employ backstepping to transform the system to this target system. And then we have to deal with D, which is the error due to quantization. So we actually then can show that after the initial time interval where we increase mu so that the state gets within the quantizer's range, which amounts in establishing this, then the solution satisfies an ultimate bound over capital D time units, where capital D is the time interval where mu remains constant, and this omega is less than 1. So if we repeat this, we eventually get asymptotic stability. And we can extend this also to input quantization. Okay, this is a simulation example. So we consider a typical rectilinear quantizer. And this is the response of the closed loop system. So with the dash, we see the switching zooming variable mu. And this is the state of the system that converges to 0. And this is a case where we have quantized, sorry. Yeah, this is the quantized measurements. This is the same, but showing how the quantizer affects the measurements. Okay, and this is the last topic I'm going to talk. So now we will consider a switched linear system with an input delay. And here we consider A and B be the matrices that depend on the switching signal. And we consider a setup where the switching signal is actually unknown, and it features a dual time, but this dual time is arbitrary, it's not restricted. So in order to design a predictor-based controller to compensate D, the main challenge is that we don't know the future values of the switching signal, which will be needed to construct the exact predictor state. So the exact predictor feedback controller is inapplicable in that case. So we would like to overcome this challenge. One way to do it is as follows. So we consider an average system with matrices A bar and B bar, and compute a predictor state for this average system, and then compute the predictor feedback controller corresponding to this average system. Now, for instance, A bar and B bar could be element-wise mean values of the respective A and B matrices, or given by an optimization, solving an optimization routine. So there are ways to choose such A bar and B bar. But the idea is to use such an average predictor-based controller. Now, with such an average predictor-based controller, we can prove the following. So if the average system is controllable and there is a gain that can stabilize this average system, if all matrices A and all matrices B are close to the respective expected values A bar and B bar, then we preserve uniform exponential stability under the average predictor-based controller. Now, this limitation, this theorem doesn't restrict D or tau D, but it restricts the differences of the matrices from the expected values, and this is a limitation that is expected because otherwise the prediction accuracy cannot be sufficiently small to guarantee stabilization. So there is nothing else you can do. Now the proof actually goes as follows. So one has to construct first the exact predictor state, which is inapplicable, and then basically compare the exact predictor feedback controller with the average predictor-based controller developed, and show that this error can get sufficiently small when epsilon is sufficiently small. So all this do this. So I'm skipping all that. And this is just a simulation example to show you how this works for a system with two modes. So this is the evolution of the state and the control input with the average predictor-based controller. And this is, the response when, because one may say, okay, if every system has to be essentially close to the other system, why don't you apply a predictor-based controller assuming a fixed mode? And because the performance won't be as good. So these are the performances when one does that. One employs a predictor-based controller corresponding to a fixed mode predictor-based controller. And we have recently also tried to improve the accuracy of the prediction state, exploiting potential knowledge of the switching signal. So if we know some dual time, then we can actually construct more accurate predictions of the state because we know some interval that the switching signal doesn't change. Okay, and we are currently working on hyperbolic systems without the input quantization, and we are also trying to extend the results of the switch systems with input delay to nonlinear systems or state-dependent switching. And with this, I would like to thank you once again for the invitation and for your attention.